So this is roughly the idea of Riemann integration. Now let us start working it more systematically. So from now on, we start with the formal, far more rigorous statements of this. So we make, let me just discuss the assumptions. Assume the following. F is a function defined on the interval AB or 2. I assume this is an ad hoc assumption which I will take out later at the next level. I assume f is greater than or equal to 0. Now here I assume minus infinity. This is a finite interval that I am talking about. A. It's a finite interval that I am talking about. I make these two assumptions. Now I also assume that the third assumption that I make is f. What does it mean? That is, there exists capital M positive such that 0 is less than or equal to f of x. So let P be a partition denoted by x0 equal to a less than x1, or I write a equal to x0 less than x2 less than xn minus 1 less than xn equal to b. So this partition I write P. What does it mean? It means you have a set of points x0, x1, x2, etc., xn minus 1, xn. Satisfying this particular inequality which induces a partition on the interval AB, as I have seen in the figure. So this is taking the interval AB, and then I am writing this as x0, and then I have a point x1, I have xi minus 1, xi, and then xn minus 1 and b equal to xn. This is the partition that I have. Now I define small mi to be equal to infimum of over the interval xi minus 1 to xi of f of x for I equal to 1 to n. And so also let me define m capital Ny defined as, these are all definitions, supremum of f of x on the interval maybe for the case and I equal to n, you can write n as the infimum taken over the closed interval xn minus 1 to xn, that is xn minus 1 to b, and similarly, but that is immaterial. Now we define two functions. That is the step function that I have defined here. Let me define it in this way. So I define a function associated with f, therefore I use f here. So I denote this by FLP subordinate to the particular partition you have. I define the function to be sigma I equal to 1 to n minus 1 mi, a characteristic function of the interval right, plus on the last interval I take this as mn, characteristic function of closed intervals. Similarly, I also define F P M. This is the upper step function that I have introduced, which is equal to sigma I equal to 1 to n minus 1 capital Mi chi of. What is this chi? Chi is the characteristic function, or what we call the indicator function, which is defined as chi of A is defined as equal to 1 whenever x belongs to A, and this is equal to 0 when x belongs to A complement. So this is the definition. What does it mean? Let's examine one of these. When you take chi x n plus n minus 1 xn, now you see that, let us evaluate this f at some point. We evaluated this at some point x on the interval xi minus 1 to xi. Then what happens? Only that particular term will survive, because chi xi minus 1 to xi will be at that particular point will be equal to 1, otherwise everywhere else it is going to be 0. So the value of the function will turn out to be simply small m1. Similarly, f p m evaluated at x, and if x happens to be in the interval xi minus 1 to xi, then you see that the value of the function will be capital M1. So that is the step function that I have. So now what we want to do, so we got two step functions, and these step functions squeeze the function, the f between. Okay? Now let us compute the areas corresponding to this. So we immediately infer the following. What is that? We have the inequality, and that is, see, these are little things that you have to put your hand on and try to prove them. So what is the thing that you have to work on? You see that you have the inequality, immediately you have the inequality that 0 is less than or equal to f of and this, you know, is everywhere bounded by the number m, because that is the bound that you are set for capital M. So you prove this. Give a proof for this. Now let us compute the area. Area of F L P. This is quite easy to compute. If you look at this function, it is going to be mi times the length of the interval summed up plus mn times the length of this interval. So I write this as sigma I equal to 1 to n small mi, and similarly the area enclosed between the curve F P M and the x-axis computes to be equal to sigma I equal to 1 to n capital Mi. The consequence of this is that, and let me use a standard notation, I designated this by L, P, F, and this by the U, P, F. And this is the short form for the following. LPF is the lower sum associated with F for the partition P. This is UPF is the upper sum associated with the F corresponding to the partition P. And you have the following, that is L. This is what this inequality is there. And this is also bounded by m into b minus b. Once again, prove. These are things to be proved. And there is nothing, no sophistication involved here, just quickly compute whatever is there. That's all you have to do. Therefore, we have this inequality. Now we make an observation. Make the following observation. Suppose P1 and P2 are two partitions of AB such that P1 is contained in P2. That means every point that is there in P1 also appears in P2, and P2 may contain many more points. This is the assumption. So we are talking about points on the interval AB. Then you make the following observation. You see that L P1 F is less than or equal to L P2 F. This I have already said, that you have to prove this. Okay? Why this happens is because the approximating curve moves up towards the function, gets closer to the function when you induce more points on the interval. This is the reason. Similarly, you have U P2F, this is moving from above, is less than or equal to U P1. This is quite easy to see. What is happening is that take the interval AB on which you have a curve like this. Then you see the first approximation is this is your LP. So this I call xi minus 1 xi. Then this is LP. Yeah, this is, and this area is UPF. This area is UPF. So you have an LPF, you have a UPF, and the actual area is squeezed between the two. Now when I introduce an additional point here, signs like xi star, what I have seen is that I have a new step function defined, and the area, the new area corresponding to the new partition is going to be something bigger than the lower approximation, is going to be something bigger than the earlier one. Similarly, the partition that I get here is going to be, again, you are going to lose some area here, which means your step function will move closer to the actual function. So that's the reason for this inequality, and that you have to prove explicitly. We have this inequality, that means 0 less than or equal to L P1F is less than or equal to L which is less than or equal to U less than or equal to M into B minus. This is the inequality. So you see that with refinement, the upper sum has moved closer to AF from above, and the lower sum has moved upwards towards AF. So what do you get? Now we make another observation. The other observation that you make is this. Suppose P and P tilde are any two partitions, we can prove that this inequality is there. How do you prove that? It is proved using the following fact. That means if you take P union P tilde is a refinement of. Therefore, what is that you end up with? For arbitrary partitions, we have 0 less than or equal to L, P, F, which is less than or equal to A, F, less than or equal to U. The same thing holds with P and P tilde, which implies, suppose is the class of all partitions of P. What do I mean by that? It's a set of finite set of points satisfying an inequality of that kind. These are all numbers that you compute associated with F and P. So you look at the collection of all numbers L of the lower sum. So also you look at the collection of all numbers U. What can you say about this? See that this whole set of numbers is bounded above and this whole set of numbers is bounded below. So both are. So this is bounded above and this set of numbers is bounded below. These are real numbers. So you get a set of real numbers which is bounded above. You get another set of real numbers which is bounded below. Analysis comes into play, properties of the real line that comes into play, and it says that if this set of numbers is bounded above, there is a least upper bound or supremum of, and so also these are bounded below, therefore there is a greatest lower bound. Okay, these are all bounded below, there is a greatest lower bound. Therefore what you have is the infimum of P belonging to P. Now let me denote these two numbers by, I designate this by integral a to b fx dx, and this I designate by integral a to b top bar these numbers exist. And this I call the lower integral and this I call the upper integral. Equal to supremum of and similarly this is upper integral both these up the supremum and infimum exist. Because if you have a set of numbers which is bounded below, then certainly the infimum exists. If you have a set of numbers which is bounded above on the real line, then the supremum exists. This is basic analysis. And also we have the following inequality. So I call this upper integral. So this is the lower integral. This is called the upper integral of now from that basic inequality, it follows that integral 0 is less than or equal to the upper integral a to b. This inequality holds. I mean, all these various statements I have made has to be supplemented with a few lines on the argument. So we have got a very interesting inequality related to this. So the question that you ask is, are they equal? Could be equal. They may not be equal. So the question is, do you have equal to this is the question. I'll make a small investigation on some example. So let me define the function. A set of fractions, and this as 1. The set of irrationals on the interval 0. Now this is the famous Dirichlet function. Now you compute the upper sum and lower sum corresponding to this. If you compute the upper sum, you get the following. See, you get 0 equal to integral a to b. This is equal to 1, because the reason is that if you take any interval on the interval 0, 1, you will get a rational point, an element of q, an element of q in it. You can also find an irrational point on that. This is something very, very interesting about the structure of the real line. That you take any interval on which you have infinitely many rational points and infinitely many irrational points. And the function that we have defined, unfortunately you cannot draw the graph of the function, takes the value 0 at all rational points and takes the value 1 at all irrational points. Now you compute the lower sum and upper sum. The lower sum turns out to be 0 for any partition. So also the upper sum turns out to be 1 for any partition. And therefore what you get? You have a function which is a bounded non-negative function, the type of function that we have been talking about, where the lower integral is different from the upper integral. But there are several functions where the lower integral could be equal to the upper integral. And in that case what we have, so we say that, so we make a definition. F is Riemann integrable, or integrable in the sense of Riemann, and integral, the lower integral is equal to now this is the definition of Riemann integration for a non-negative function, bounded function defined on the interval. And we see that this is not something that is assured for all bounded functions. Okay, therefore there's quite a lot of questions that pops up at this stage, which we'll take up in the next lecture. So thank you very much.